So that was a little bit of the Bode mood preset, which uses the final category of parameters we'll talk about, and those are related to static friction. In addition to viscosity, the fluid friction that we've talked about so far, the kinetic model also includes a static friction component. One way to think of this is that the mass is also rubbing on the sides of the walls in addition to being affected by the fluid friction of the liquid inside the container. Let's go to our PHET simulation for static friction. This is a wonderful site that we used for the simulation of the model so far. They have a number of different kinds of simulation here. Static friction is the friction most of us are well acquainted with. A classic simulation for this would be to have an incline that you can create with a mass on it. There'll be some coefficient of friction, a parameter that you'll define that will affect the stickiness basically of that object to move in response to the force of gravity. For example, let's remove static friction entirely. We have a mass. We'll increase the incline just a bit, and that mass starts to roll. As you can see, the person wasn't applying any force in the opposite direction, so once that mass starts going, it will continue. So without friction, even just a little bit of angle will cause the mass to start moving. Now we'll apply a coefficient of friction in the kinetic model. That will be like applying some degree of static friction. Now I can raise the ramp and nothing will happen. I can get to a point, if I raise that ramp high enough, where the force of gravity will overcome the friction, and the mass will start moving again. Now I can apply a force on that to overcome the motion, in which case I'll have to increase the angle even more, and at some point the force that I'm applying won't be enough to stop the force of gravity and that mass. I could make the mass smaller, and now the man has plenty of force to keep the mass where it is. But if I increase the mass, the pull of gravity will at some point be too much to stop the mass from moving. This is greatly oversimplified, of course, but it's what's behind the static friction component of the kinetic model. So let's talk about the basic static friction setting. This is only set in the model on the static friction column. Static friction only is available from the matrix. It defines the static friction. This sets a minimum force to be applied before the body starts moving. Note that for high values of this parameter, the spring will often not be able to move anymore. Also note that for a higher mass, a greater force will be needed to start the motion. Let's go back to our pulsed model and see how this might affect that. I've turned everything off here except for the static friction column, where I will put a barrel to control that. I'll set it to 0 initially. In other words, turn off any static friction component that will be applied. Remember, viscosity still will be applied. These two can be applied in conjunction with each other or separately, by the way. So I've set up a sound that has a pretty low viscosity, so it will ring out for a while. Let's set static friction to a relatively high value and see how that might affect things. You can see our sound was terminated abruptly. It had enough force to begin with to overcome that static friction, but as the waveform gets attenuated because of the fluid friction, it will come to a point where that static friction component will be strong enough to basically damp out the waveform. Let's set the static friction lower. I've also added the ability with the gen to control the force of my pulse that we'll talk about in a second. Now with this lower value, my waveform should ring out longer as it has more force before that static friction threshold kicks in. And that's what happened. It went on quite a long time before static friction damped it out. Well, let's keep things the same, but let's bring down the initial force of that signal. Static friction should kick in even sooner now because I've reduced the force that needs to be overcome to let that static friction component kick in. And that seemed to be what happened here. Now I can turn static friction all the way up, raise our force a bit, and what we'll do is we'll set this so that we have no viscosity at all, no fluid friction. Static friction should then apply itself based on the force of the waveform. Static friction should still kick in if that threshold is reached. There, static friction can still damp out your signal, as you can see here, even if you have no viscosity applied. And there are two other important parameters that are associated with static friction that are intended to make static friction really useful in the model. These are slipping friction and quit slipping speed. Slipping friction defines the friction occurring once the body has escaped the static friction. This friction is fixed, not depending on the speed as for the fluid friction. The value is 0 to 1, expressing a portion of the static friction. 0 means no slipping friction, and 1 means that the dynamic friction has the same value as the static one. It can't be higher. Now quit slipping speed. After the spring has escaped from the static friction, when its speed is reduced to a certain value, the speed threshold, it will stop again. The quit slipping speed property sets this minimal speed. The threshold speed is never 0 inside the model, even if 0 is set on the quit slipping speed, which only sets it to its minimum value. Slipping friction and quit slipping speed have constant values that can be set in the kinetic modeler and then adjusted like other parameters we've seen using a column value. I've set barrels up to control all these. The slipping friction then is a control that you use on the part of the waveform that escapes the friction. So if we have some waveform or some input signal that we apply static friction to and we damp at the threshold, the slipping and quit slipping speed parameters are going to be applied to the portion of your sound that is not damped by the static friction. The portion we can see here that basically applies before the static friction coefficient, that threshold, kicks in. So I should be able to now have a secondary static component applied to this part of my signal by changing the slipping friction that will increase the friction on that. Let's try that. I'll bring up the slipping friction. You can see that I've basically damped that out very quickly as I bring up slipping friction. I can get that to a point where it basically damps out everything, and then I can lessen that and go back to my original waveform, the sound that I had when only the static friction was applied. Obviously, slipping friction is not something that is intended to be used in this static environment. It's best used when you alter and vary it to kind of emulate perhaps the variable friction that would result from when a violin bow is drawn across a string with rosin on it, which we'll see there's a bowing component that's included to allow you to do just that kind of a thing. Now, the quit slipping function is more a frequency dependent component that you can apply. In the static model here, where we're just pulsing and not doing much with frequency, this won't have much of an effect other than to damp out, kind of like slipping friction. Let's try that. Put a little bit of static friction on and we'll bring up quit slip function. I'll bring it up. We can kind of hear it starting to damp out. until it's damped completely. I can remove it now and go back to my long signal. So in this simple pulsed model, these more advanced static functions don't really give you much of an advantage. You could probably do most of what we just did just using the viscosity control. It's when we start applying these things to dynamic waveform inputs that we really can do some really nice things. A primary use of these slipping friction functions is to allow the kinetic model to create slipstick effects. We're all aware of the sounds created when two objects move against each other as they come into contact, sometimes slipping and recatching perhaps. Think of the windshield wipers in your car squeaking as they move across a semi-wet windshield surface, or a door creaking from the sound of the hinges rubbing each other perhaps. We've already talked about the violin bow on a string. That's a classic slipstick effect. This slipstick effect occurs as soon as the static friction is greater than the sliding friction. Depending on the material, this leads to the activation of vibrations, which are emitted as squeaking, creaking, cracking, rattling. A lot of different kinds of sounds can be created using this effect. Now this slipstick function can also be referred to as stick slip. I've brought up the utilities kinetic slipstick filter preset that Christoph wrote, and we'll play around with this for a while to illustrate some of the things that we're talking about here. Let's look at this preset. There's a kinetic bank that's defined. Now the static friction is set to a constant here of 0.2. Perhaps we'll make that controllable with the gen a little later. The frequency component of the model is set to a barrel controlled value. A spring constant is set to 0, which is totally controlled by a barrel. And the quit slipping speed and slipping friction are controlled by barrels as well. Now a sine wave is set up to send into the anchor, as we've seen before. Now the output of the kinetic model is sent into a high-pass filter, and that, you can see, is then sent to the outputs. And Christoph points out that because we have gravity here defined, if you use gravity, that creates a small constant DC offset. So adding a DC cut, in this case a high-pass single-pole filter with a very, very low cutting frequency, here set to 1 Hertz, may be a good practice. And we'll see that some of his presets that use the kinetic model do just this. Before we dig in, let's just go back a second and review the difference between how we pulsed the model in relationship to static friction and now what we're going to do by using Z pressure as the basic amplitude control. When we pulsed, we started with a very high force, and there'll be some area in here where the static friction needs to be overcome for sound to be generated. Because we start with such a high force in the pulsed model, right from the very beginning we're generating sound. As we applied viscosity, the waveform damped, and at some point we went under that threshold where the static friction will damp the sound. And that's kind of what we saw in our waveform when we looked at the pulsed model. Also, something to be aware of is when we have gravity defined, that's going to create a pull on that mass, and you will not get complete symmetry in the waveform from bottom to top. Things will be DC compensated, as Christoph mentioned, and there could be some amplitude asymmetry involved here where the mass will hit the bottom of the edge first, and maybe in some cases might just hit the bottom over and over again instead of hitting the bottom and the top. And perhaps we saw some of these asymmetries when we were looking at padding and elasticity. When you went in one direction, you could see a big change, but in the other you did not. We can easily see this effect of gravity affecting the waveform, pulling it down and imposing this asymmetrical structure. I'll start with a sine wave and then bring up gravity, and it will be immediately evident. it gets to a point where gravity overwhelms the system and no sound results. But you can see how gravity both distorts things and creates this DC shift. Now, when we look at presets that are not pulsed, but use Z pressure for control of amplitude, and probably most of the kinetic presets in the library are of this nature, we have the opposite happening. Here we have more of a traditional threshold for static friction taking over. If we apply a very light pressure on the fingerboard, we might not create a force that's great enough to exceed the threshold of our static friction, or stiction as it's sometimes referred to. Very much the same as in our simulation when we raised the incline and the mass didn't move because the force was not enough to overcome the static coefficient of friction of that mass. What this will mean is that at a certain low pressure level on the fingerboard, if you have this static friction defined at a high enough level, you may not get any sound until you press a bit into the fingerboard. Now, of course, if you press hard enough, you will very quickly get past that static friction threshold, and then if you continue pressing hard, you'll constantly be above it, and you'll get constant sound coming out. Now, it is possible your waveform may be in and out of that threshold area for very small amounts of time, and in that case, the static friction threshold may take over and have some kind of a rattling effect or discontinuous effect on your sound. Let's go back to our preset. We'll put a parameter on the static friction column. We'll use a free Gen 1 for that. We'll go into our editor. We'll say Gen 1 equals stiction. Then we'll define a formula. We'll set that to Gen 1. We'll set that from 0 to 1, and we'll put that on the static friction column. Now, I'd like this to start at the 0.2 that I had before, so what I'll do is I'll go down here to the bottom left, I'll show formula value, and I will play a note, and I'll raise this up till I get to 0.2, just about 0.2. And now what I'll do is I will save this. I'll put that back in my user presets, and now I've parameterized that and I can change it. Let's start by removing the output of the kinetic model, and I will just output the sine tone that's feeding it. And what I'll do is press very lightly on the fingerboard. You can see on the display there, I can very faintly hear that sine tone. I'm pressing very lightly, as you can on the Continuum. Let's remove that, and I'll turn on the kinetic model, and now let me press the same way. Nothing. In fact, I can press quite a bit harder, and finally I hear a sound. Well, why is that? It's because I have that static friction set to a value where I have to give it more force to overcome that threshold. Theoretically then, I should be able to lower my stiction amount, and I should get a sound pressing much less hard. And that's exactly what's happening. I can hear it at a much lighter pressure. Now, if you notice the sine wave input to the kinetic model on the anchor, that formula actually offsets by 0.2, which is the amount that was initially set as the static friction threshold. There's some interpolation on this to smooth out the input, but if we removed that 0.2, we would have to press even harder, because only Z now is controlling the input to the anchor. And you can see I have to press pretty darn hard now to get any sound out. Obviously, why that 0.2 is used as a constant offset on the input to the kinetic model in this case. So there's the first thing that we have to understand. This stiction, static friction threshold, is going to be pressure based when I have a Z pressure function that's riding my preset. Now we can set things back to the original. So obviously the stick slip, which here is the quit slipping friction function, and the slipping friction itself, I can change those to my heart's content if I'm just pressing lightly. I have no sound. Let me change those. Nothing. Nothing. Why? Because those only apply to the sound that escapes the static friction threshold. The tuning function here is just basically a fixed frequency that you can set with your barrel. And as we saw in a previous video, this is going to affect the spectral peaks that might develop when I play a sound. The harmonic content of that sound, it's not going to change the bass frequency. That is controlled by the frequency of the sine wave, the X-controlled sine wave that's feeding my model. Well, let's play around a bit more. As you might assume, some of the kinetic model parameters are tightly coupled with each other, as we've seen in previous videos. Let's take the spring constant down to 0. So the spring has no stretch on it at all. It's not going to create a sound. Let's bring that up. We're tightening the spring, putting more tension on it. And at a certain point, will be past that static threshold, will create a sound. You can see I have to press quite hard. I can continue tightening that spring. A tighter spring should create a greater force. And you can see as I increase the spring constant, I have to press less hard. I can get it to a point where only a very slight pressure gets a sound. So this is one way to counter the effect that we had before, where we had to press harder to get to a certain point to get past that static friction threshold. We can use spring constant as a method of adjusting the pressure sensitivity to get past that threshold as well. More than one parameter change in the kinetic model will cause a force increase that will get you past that threshold. Let's try and get a feel for what these static friction components do to the sound. We'll turn off the static friction threshold, the quit slipping speed, and the slipping friction. We'll just listen to the sound of the tone that results. Here we have our fundamental and that spectral resonance, that spectral peak that is created by moving the frequency component around. Let me move that around a bit and you'll see it'll make a big change in the spectral content of my sound as we discussed in a previous video. You can see I can move that spectral peak around by changing the frequency value. Also, as I press harder, I'll put more force on that mass, and you see the spectral content also increases. Now we'll turn the static friction threshold on and see how that affects things. Well, you can hear and see as parts of my spectral content move in and around that friction threshold, I'm hearing almost a static-like noise effect as some of the partials are above that threshold and come out clearly, and others are on the threshold moving in and out, and we get that kind of staticky sound. What if I lower the threshold? You can hear, as I lower the threshold, more and more of those spectral components are above the amplitude where they're going to get damped by the friction, and I have less of a noisy, staticky sound resulting. If I raise that threshold too much, I'll damp out all the frequencies. There, as I raised that threshold, more and more of the harmonics that were above that threshold no longer were, and we got even more of that static, noisy effect coming in until the threshold was so high, all of the harmonics, including the fundamental, were beneath it, and then everything damped out. So you have to be careful on the setting of that static threshold. Set it too low and not much will happen. Set it too high and you'll damp everything out. Let's now apply some slipping friction. We're already applying the static friction threshold. We can see in our output this area where the static friction threshold is taking control. Certain harmonics are on the fringe of being in and out of that area, and we get this static sounding instability resulting. We also have a spectral peak in here caused by the setting of our frequency. Let's bring up slipping friction and see what happens. You can hear slipping friction was being applied to this area that escaped the static friction threshold, and we had even more instability going on there. That static friction noisy oscillation is still going on because there's still going to be components that are going to be affected by that. But now all those harmonics that are at an amplitude high enough to escape the static friction threshold, the slipping friction will now be applied to that area. So depending on the setting, we almost can get a double oscillation going on there. An overlapping and interaction of these two static noisy components that create an even more complex sound. You'll also notice that as I raised the slipping friction, that spectral peak started to disappear, because that slipping friction also has a damping effect, and as I raised it high enough, that spectral peak all but disappeared. But of course we still have this area of instability that's caused by the static friction component to begin with, in combination now with the very highly damped slipping friction component. Now let's look at the quit slipping speed function. This is a frequency dependent function. The lower it is, the lower the frequencies it starts applying this sticking function to. So as I change this, the frequency at which it comes into effect will raise higher and higher. This will be evident when I play an example. Here this stick slip function, which is basically the quit slipping speed, is set to 0. Of course, the static friction threshold's applied, we have some slipping friction applied, and now I will raise the stick slip function, the quit slipping speed, as I go up the fingerboard. And you'll see, as I raise this, it will stop affecting so much the bottom frequencies, but kick in more on the top ones. So there I'm playing a low note. This stick slip is set to minimum. Let me raise stick slip a bit. It doesn't seem to affect the lower note anymore, but as I play higher, I can hear that static frequency shifting going on all the way up. But I've raised past the point where it's really affecting me at the low frequencies. Let me raise it a bit more. There, you can hear when I raised it past the frequency point where I'm playing on the fingerboard, that static sticking slipping motion went away. But it applies when I go higher. I can raise it again and get past that point. I still have that static friction threshold applying. I still have slipping friction applying. But I'm even more contorted when that stick slip function's involved. There, I've just raised it to the point where it's not so much affecting where I am now. Now, you wouldn't normally use it that way. In practice, you dynamically change it so that it's sticking and slipping and sticking and slipping on you. Slipping friction is often used in conjunction with the last thing we'll talk about, and that's bow speed. Now, this stick-slip mechanism is really a result of kinetic or dynamic friction. That's this friction that results after the static friction force is overcome. Of course, the higher the mass, the more you'll stick. Now, in the kinetic model, the floor can actually continuously be moving with the concept of bow speed. This can be set positive or negative to simulate moving in one direction or the other. In a sense, you're bowing the mass, but really the floor is moving. You can also move the floor by changing height in some dynamic way, of course. So bow speed or ground speed is the speed of the motion of the contact surface from which results the static friction. The sign of the speed defines the direction of the motion. A value of 0 means no bowing. This parameter has no effect if static friction is not set. So I've gone in and modified our preset a bit. I'll set height to 0 here so I can control that completely in the matrix. I'll set that to its full value to start. Quit slipping speed, I removed as a barrel. What I'm going to do is create a little formula. I'll set an initial offset on that on W, and then I'll control it from there with Y. So we can still have that static kind of a sound. I've sent in now a little different waveform. Instead of a sine wave, I've sent in something a little more complex. There is no slipping friction applied anymore. But I've set a shape generator 9 times a second. I've set a formula that uses that, controlled by the Gen 2 barrel that I've set to bowing, and I set that to a sine wave that will output both a positive and negative component. So now let's bring up the bowing, none applied right now. And as I bring that up, I should induce a sine-like oscillation based on moving that floor in this sine pattern. You can hear that changing. Let's change that to be lower. You can hear there's a background static oscillation in addition to the bowing speed. Higher value. Here we have more of an effect than trying to use it as, say, a violin bow. Let's end by looking at a much more subtle example of the use of bowing and static friction components, the bowed mood preset. Let's quickly run through this. It starts with the kinetic model with some slipping friction and quit slipping speed applied as constants through the kinetic modeler. No elasticity or padding. Pretty high viscosity. The height of the container is rather low. No gravity, a little bit of mass, and relatively large spring constant. This is a waveguide-like preset where the output of the kinetic model here, bank A, you can see is fed into a low-pass filter on filter 2. That's sent to the left output. The output of the kinetic model, though, was also set into a feedback loop using this voice delay. Bank C, you can see, is fed into another low-pass filter, filter 1, and that is sent to the outputs. But the output of that voice delay is also sent into that high-pass filter we talked about, that very low-cut single-pole high-pass filter. And the output of that high-pass filter, filter 3 here, that is then sent into another low-pass filter, which in turn, filter 4 here, is sent back into the kinetic model. So there we have this very long filtered delay loop that's initially triggered with a pulse on the excitation input. The resulting sound is this very nice stringy kind of effect, which is made more resonant by the use of our recirculator that uses a digital echo. with a high-pass filter. A little bit of this is also sent for some convolution as well. So it's a pretty complicated preset, but we really want to center on the bowing and static friction components of this. Let's just listen to the sound a little bit. That major oscillation is really caused by a triangle-shaped shape generator that is controlled by barrel 2 on the static friction component. It's called stiction modulation in this case. I can bring that to a very low value. Or I could turn it off entirely, maybe for our purposes, because there's also, you can see, a constant applied of 0.3 that starts out that static friction value. So let's take that off for our purposes, because we really want to concentrate here on what the bowing effect sounds like in relationship to the quit slipping speed. You can hear we've removed all that oscillation caused by that modulation on the static friction threshold. Now let's look at the bowing. A constant value of 0.5 is sent in as the speed for that bowing. Let's increase that value. You can hear that it changes. Let's decrease it. Now it's very, very, very faint. I can apply vibrato on the fingerboard, of course. Let me increase it a bit. And you can hear as I bring that speed of bowing up, it does have an effect. A lot less noticeable when I had the static friction modulation there. You'll also notice on the frequency column, there's a barrel that is labeled harmonics. I can change that harmonic content as we've seen a number of times. Before we saw when we changed that, we were just changing a spectral peak, but because this is being fed through this delay loop, you have a much greater effect on the harmonics of the preset now. Obviously, if I lower that too much, it's not going to sound like a string anymore. And we have quit slip threshold control, as you see here, on Y. You can hear that's a very subtle effect, the way it's programmed here. I can bring up the stiction, that's barrel controlled on this offset to the static friction. And you can hear it creates a more complex harmonic sound in this case, again, because it's all being fed through that feedback loop. So there's a really good example of the use of the bowing and static friction components in a preset. Now we've presented pretty much all the components of the kinetic model, quite a lot for you to take in, quite a lot of options to create a wide variety of sounds. And I hope this has been of some use to everybody to try and understand the kinetic model a little better.